Hello and welcome. This will be a video about instrumental variables. In this video, I will provide a few examples of endogeneity. Then I will talk about endogeneity definitions. Then we will talk about instrumental variable setup and the models, and the two-stage least squares estimation procedure on how to deal with these endogeneity issues. And then we will talk about identification issues and endogeneity tests and weak instrumental variables. And finally, we will conclude with systems of equations when we will talk about the two-stage least squares and the three-stage least squares. So here are a couple examples of endogeneity. First, wages and education jointly depend on ability, which is not directly observable. So in this case, we may want to have a regression of wages on education. But the problem is that the ability is correlated both with education and with wages, because higher ability would lead to higher education, hopefully, and that would lead to higher wages. So in this case, we have an endogeneity where that ability, which is not directly observable, would be included in the error term. And we can use, for example, available tests results to proxy for ability, and we would call these instruments. Another example which is very popular is consumption and income that are both determined by macroeconomic factors. So you can't say which one causes which, consumption or income. And then we can use investments, say, to control for endogeneity. So here are a couple of causes for endogeneity. First one, when the explanatory variables are measured with errors, and we have just variables that are not precisely measured. And the second one is when we have reverse causality, and this is when the explanatory variable would be caused by the dependent variable, so going the other way around. So here are definitions of endogeneity. A regressor would be endogenous when it is correlated with the error term. Let me provide a simple example here. In this case, Y would be earnings, X would be the years of schooling, U would be the error term, which would include this ability that is an unobserved variable, and Z would be the proximity to college. And in the first case, where I have exogeneity, and this is when the regressors X and the error term U are independent causes of the dependent variable Y. So in this case here of exogeneity, we have X here causing Y, and U, the error term, causing Y. This is the best case when we can just use OLS regression to estimate the model, and we are all set. However, in the case of endogeneity, we would have that the error term U is affecting the regressors X and therefore indirectly affecting Y. So what's happening is we're adding an extra link here from the error term to the regressors. And this is, for example, when we have this unobserved variable ability that not only affects how much wages or earnings you're going to get, but it also affects how many years of school you get. And in this case, we have endogeneity where here there's this extra link, and that's not good because it causes biased results. So one way around this is to use what is called instrumental variables. And instruments Z would be associated with X, but not with the error term U. And here these Z instruments come into play. And for example, this will be proximity to college, where you live and how close you are. So if you're very close to college, then that will probably affect how many years you went to school. However, that shouldn't affect the wages here, nor should this variable be included in the wages equation. And this is when we have a perfect variable here as an instrument. And we're going to use the z variable to correct for this endogeneity and remove that effect from the fact that u is correlated with x. And then we would estimate the equations where we have, so to speak, removed the endogeneity of the endogenous variables. So here are a few requirements for the instruments z. So z must be correlated with the regressors, and the expectation of z prime x would not be equal to 0 in case z would predict or cause x. Why is that important? Well, because if you have instruments that are completely irrelevant to the regressors or to the endogenous variables, then what's the point of having them? We want to have correlation with them, and we want to have like somewhat strong correlation with them. The second requirement for a good instrument is that z is uncorrelated with the error term. And here the expectation of z prime u would be equal to 0. And this means that z itself is not endogenous. So the goal here is to find instruments that are not correlated with the error term, that would influence the regressors, and will not be included in the equation for the dependent variable. Now, that's probably the toughest thing here, is to find good instruments. It's very hard to do that. And the last one is that z is not a direct cause of the dependent variable y. And here's the covariance between y and z given x would be 0. So z would not be in the y equation. So again, z would predict or cause x, z would not be endogenous itself, and then it will not belong in the y equation. Again, this procedure is very nice and very easy to do. The hardest thing about this procedure is actually, in real life, is finding good instruments. So that will be a challenge even in your problem that you're doing. So let's go ahead and talk about instrumental variable setup. First of all, consider the linear regression model, y equals x beta plus u, right here. And this is the normal equation for an OLS or linear regression. And the endogeneity, again, would be when one or more of the independent variables would be correlated with the error term, and here we would have that covariance not being equal to 0. Well, what's the problem with that? The problem is that the estimated coefficients from the OLS estimation would be biased because they would be equal to beta plus this expression. Well, if the expectation of this term here is not equal to 0 because the regressors are correlated with the error term, then we would have that the expectation of b won't be beta anymore, and we would have biased estimates. That's not a good thing. So now, instead of just using this model here, the linear regression model, let's use the following structural equation, and here I'm forming the terms. y1, we would call this the dependent variable. y2 would be the endogenous variable, and x1 would be the exogenous variables. So instead of just calling all of these x variables that belong in the equation here, we would split that in two. These y variables, and notice that we use y, which is typically reserved for a dependent variable because it is endogenous. So these would be, again, the endogenous variables. These are the problematic variables that we need to do something about. And these would be the completely exogenous variables. So there's nothing to be done about those variables. So the structural equation model would involve a combined set of y2 and x1 of both endogenous and exogenous variables, and we need to find a set of instruments z that contains x1 and x2 here of only exogenous variables, where x1 would be an instrument for itself and x2 would be an instrument for y. So you see this x1 here, it stays here in the equation. And instead of using y2, we would be using x2. We need to find these new instruments for the fact that the y2 would be an endogenous variable. So what is this two-stage least squares estimation procedure? Generally speaking, we would replace the endogenous variable with the predicted values of this endogenous variables when regressed on the instruments. So more specifically, here is stage 1, the first stage, or the reduced form equation with only exogenous regressors. So now the first stage would be this y2 variable, the endogenous one that causes problems. We would regress that on the x1. These would the truly exogenous variables from the structural model equation. And x2 would be the instruments that only occur in this equation but don't belong in the original equation. So once we estimate this equation, we could save the predicted values here, and then we would substitute them in the structural equation model. So this was the structural equation model, and instead of the original variable y2 that we had, now we're going to use y2 hat, and that one comes from the first stage equation. So here hopefully we would correct for endogeneity by using its predicted values. So that's it. That's the whole philosophy of using the two-stage least squares estimation procedure. So now I will talk about the identification issues. The first one is the order condition, where the numbers of omitted instrumental variables must be at least as large as the number of an endogenous regressor. And the second one is that the rank order condition, that the matrices Z prime X must have a full rank in order to be inverted. And so this way, if we have one endogenous regressor, you need at least one instrumental variable. It could be more, but at least one. You can't have less than one. And again, for the rank condition, you need full rank of these matrices. So for the just identify model, what we would call the just identify model is that if we have one instrument x2 for each endogenous variable y2, and in this case b for IV, that's the estimate here, would be z prime x inverse z prime y, and if we replace here y with the original expression here, then we would have beta plus this. Well, the problem here, unlike the original one, we have z prime u, and the expectation of that is 0. So here we would have an estimator that is unbiased because the expectation of this would be exactly beta. So this is a very good case. The under-identified model is an IV model where we have fewer instruments x2 than exogenous variables y2. And the under-identified model would have infinite number of solutions, and therefore no consistent estimators exist. So basically, if you can't find as many instruments as you have endogenous variables, you basically can't estimate these models. For the over-identified model, we have an IV model that we would have more instruments than endogenous variables, and that's a good case. And we could use two efficient estimators with these models if we have more instruments than endogenous variables. The two-stage least squares estimator would be best if the error term is IID and homoscedastic. And here this would be the expression for B two-stage least squares, and we would have this big expression here. So even when we have two-stage least squares with over-identified case, we could estimate it. So notice that this expression is so much simpler when we have the just identified case. The next way in which we can estimate these models is using the generalized method of moments, GMM, and we would have this expression for the coefficients. And here W, that weight matrix, would be Z prime Z inverse, if we have this one equal to this one, well, basically these two would be identical. But usually this weight matrix here would be S inverse hat, where S hat would be the estimated variance of Z prime U. And this estimator would be optimal in the presence of heteroscedasticity, so a lot of people use it. Next, I will talk about the instrumental variable tests, and you need to test for endogeneity so that you can justify the use of these instrumental variables. The first one is the Houseman Test for endogeneity. So the Houseman Test would check if the regressor is exogenous or endogenous. How does it do it? It compares the OLS and the IV estimates to check for significant differences. So remember that the OLS estimate is when you use this endogenous variable just the way it came in the data. And the IV estimate is the one that is corrected, or these are the predicted values of this endogenous regressor on instruments. So what we're saying here is that if we don't use the raw endogenous variable, but instead we use the predicted values, if we regress that same endogenous variable on instruments, and if these coefficients are really different from each other, then that would be a justification for using instrumental variables, and we would conclude that the regressor is endogenous. And if there are not significant differences, basically the instruments aren't helping too much, and the estimates are very close to each other, then we would have that the regressor is exogenous. And in this case, there is no point in using IV estimates. The next test that we can use is the Durbin Rule Houseman Test for endogenous regressors, and this is the procedure that would check if the covariance of XE is not zero. So how would we do that? We could estimate the first stage model where you have Y2, the endogenous variable, regressed on the exogenous variables from the structural model plus the instruments that don't belong there. And now once we estimate this, we can include the predicted values you had from this regression into the structural regression. And here we would have, this is the structural regression where we have Y1, this is the endogenous ones, these are the original exogenous variables, and here we have this predicted values of the error term. And we want to see if the coefficient on these residuals is not significantly different from zero, then we have these regressors are exogenous. If it is significantly different than zero, then they're endogenous. So what we're saying here is that this one isn't changed too much by including those residuals. So it's just an alternative way of testing for endogeneity than just the Houseman test. So the next thing that we could check is tests for over-identifying restrictions, and this is when we have more instruments than endogenous variables. And that's hard to do, but if you have more, you're lucky. And in this case, we want to know if all of them are valid or not. And the way to test for that is to estimate a model using GMM and form the following test statistic here, coming from the GMM model. And that one would be distributed as chi-square with degrees of freedom of the number of over-identifying restrictions. And then if we reject the null hypothesis, we would say that at least one of the instruments is not valid. So we want to not be able to reject the null hypothesis. And here, if you have several instrumental variables, you might want to play with these tests until you find the instruments that are best suited for the problem that you're considering. So on this slide, I will talk about weak instrumental variables. And a weak instrument is that has a very, very low correlation with the endogenous variable, basically we want to correct for the endogeneity, but because there's not much correlation, this instrument isn't helping that much. I mean, we want a very strong correlation, but that's usually not happening in real life. We have low correlation. So if we would like to test for weak instruments, in case of one endogenous regressor and one instrument, a low correlation between the instrument and endogenous variable would indicate a weak instrument. So what we can do is just plain simple correlation between the endogenous regressor and the instruments, and then you look at the correlation. If it's very low, then that would indicate a problem of weak instrumental variables. If we have several instruments that are used for one endogenous variable, the best way to test for it is to look at the partial R-square or the partial F statistic from the first stage regression. So the regression where you have of that endogenous variable on all the exogenous ones and the instruments. So you're looking only at the coefficients, the joint significance of the coefficients on the instruments. And the instrument would be weak if we have that partial F statistic testing the joint significance of the coefficients of the instruments, or the gamma 2 equals 0 is less than 10. So this is kind of like the rule of thumb, is you look at the partial F statistic, and if it's less than 10, we have weak instruments. If it's more than that, then our instruments are not weak. And the consequences of weak instruments is that that will undermine the precision of the estimator. And so we would have that the variance of the IV estimator would be equal to the variance of the OLS divided by the correlation between the variables in the instruments. And the IV estimator would be asymptotically consistent, but it will be biased toward the OLS estimator in finite samples. And so the size of this bias would actually be positively related to two things: the weakness of the instruments, and it will also be inversely related with the sample size of the sample. So what we're saying here is that if we have IV estimator, that would probably be a little bit biased, but we want to have strong instruments, and we also want to have a large sample size. And this way we would have pretty good results, and we would reduce that bias. Okay, so the final thing to talk about here is how to use instrumental variables when we have simultaneous systems of equations. And here we could have two or more endogenous variables, and I've picked the case of two dependent variables, but you can have systems with as many equations as is required for the problem that you're considering. Okay, so here's the system of structural equation where y1 equals, and we have y2, and here we have z1. And so look at how this y2 here repeats here, and this y1 here repeats here. That's the endogeneity, is because you don't have a truly exogenous variable like the z variables here. You have endogenous variables here. So that's a problem. So how would we go about that? We would look at the reduced form equation where we would have y equals z prime gamma plus u. So not considering these endogenous regressors. So then we could go ahead and estimate either the two-stage least squares or the three-stage least squares procedure. And so how does that work? First, we will estimate the reduced form equation by OLS, and we would obtain y hat. So we're estimating this equation where we are only considering exogenous variables and instruments. Okay? And then from this equation we're predicting y hat here. And so once we have y hat, we will use these estimates y hat in the first stage to estimate the structural equations. So here everything is the same as above, except that instead of using the raw variable here, the original variable, we would use the predicted values of using all the exogenous variables in instruments. Okay? So this is exactly the two-stage least square estimates. And if you go back a few slides, you will see that that is exactly the same procedure as for the single equation procedure. Again, if the variable is endogenous, you regress it on instruments, you get the predicted values, plug it in here, and then that's the two-stage least square estimate. Now, how do we obtain the three-stage least square estimates? We are basically exploring the two-stage least square estimates that we have here, and then we would also look at the variance covariance matrix from the two-stage least squares estimates. So we would basically use this formula now to get the three-stage least squares estimate from the two-stage least square estimates. Okay, so what is the difference? The three-stage least squares would be more efficient than the two-stage least squares because it uses this cross-equation information, uses the correlation of equations, and the three-stage least squares would be inconsistent if the error terms are heteroscedastic. Okay, so this is all I had for instrumental variables. Now join me into seeing how to do this with an example and then estimating these models with different software. Thank you for watching.